This lecture will cover section 2.1 of chapter 2, an overview of calculus. First, we'll review some pre-calculus topics that we should have mastered before coming to this class. Second, we'll talk about the ideas of calculus. And then lastly, we will introduce the tangent line problem. So here are the 10 pre-calculus topics that we should know or we should have mastered before coming to this class. You want to glance at these topics and try to make sure that you know how to do problems that are related to these topics. For an example, maybe you should know how to find a linear functions given a slope and a point. You should know how to define polynomial functions. You know how to work with quadratic functions. Or maybe you should know how to make composite functions f compose g's of x. How to find inverse functions. And how to work with trigonometry functions and knows all of these basic trigonometry functions. Also, exponential functions and logarithmic functions will be heavily focused in this class. So make sure that you know all of the exponential rules and all of the logarithmic rules. All right, so what is calculus? It's a mathematical study of continuous change. It's been developed in the 17th century by Isaac Newton and Gottfried Leibniz. So they work independently, but they published their work roughly at the same time. Although they both were instrumentals in its creations, right? The ideas of calculus, but their approaches were different. To Newton, calculus was geometrical, while Leibniz took it toward analysis. So calculus is, by its definitions, is a limit machine that involves 3 different stages. It goes from pre-calculus, which is static change. It goes through the limit process. And then after the limits process, you will arrive at the ideas of calculus, which is the study of continuous change. So in calculus 1, mainly we'll focus on how to find the tangent line of a specific function at a point of interest. Let's look at an example below here. So if you're given a curve, this purple curve right here, and you're given a point, which is 1 and square root of 3. Right? Now your goal is you want to find the tangent line to this curve and goes through this point. So I will draw this line. This blue line here. So your goal is to find this blue line. So I call this point here P. Okay. So how can we approach this problem? Maybe the first thought is you pick a point. Let's say I pick a point, I call this Q at 2, 0, right? So this point Q. And I draw a line that goes through PQ. I get this red line right here. And I can use this line to estimate this blue line. Right? They're not the same, they quite a bit different, but it's somewhere that I can start. So I use PQ to estimate this blue line. And then you say, oh, they're too different, they're too far away from each other. Then the next thought could be, I move this point Q here to the point where it's closer to the original point. So say I have, this is Q1 and I have Q2, right? And if I move the X here, then the Y, this is a new point that I have. this should be Q2. Q2 should be this point right here. So I move the values closer to 1 to get a new point. And then at this point, I will draw a line from P to Q2. You can see that this black line here is still not the same as a blue line, but it's a better estimation for the blue line compared to this red line. All right, do you see that idea? So the idea is we want to move the X point that is closer to the original point. So if I have another point, let's say this point right here, I move X to this point, which is 1.1, let's say. And then I have a new point on the curve, which is the yellow one. So I saw it's Q3. And now I can draw a line from P to Q3. I created this yellow line. And this yellow line here is very, very, very similar to the blue line. It's a much better estimations for the blue line compared to the black line and the red line. So if you move your points closer and closer and closer to 1, your estimations will be much, much better. Okay. Again, we're estimating the tangent line to this curve at this point. So the line that we connect P and Q1, Q2, Q3, they is called secant lines. So we use secant lines to estimate tangent line. That's the idea. And if the point on the secant lines that is closer to the original points, that is when we have a better estimations. So we want to review the pre-calculus topics here. If you have the point P and Q, and you can see that P is the original point. The X value is C and the Y value is f of C. And Q is a new point, right? When you add a distance to the X value C, delta X. So delta X is a distance between the X values of the original point and the X values of the new point. That's delta X. And then f of C plus delta X is just the coordinate, the Y coordinate of the new point Q. Okay, you have this X here, and then you also have Y here. And this X and Y are different, so I call it different names. So then what is the formula to find the slope of the secant line PQ? The slope of the secant line equals to CY, remember, like Y2, Y, right? 1 minus Y over X1 minus X. It's just the difference of the Y values over the difference of the X value. And it will say the Y1 is f of C plus delta X minus f of C over C plus delta X minus C. So the result is f of C plus delta X minus f of C divided by delta X. So this is the formula to find the slope of the secant line PQ for these 2 points right here. Okay. So we started this problem by picking a point where the distance between the new point and the original point is 1. So I pick the point Q1 and P. So Q1, the difference between 2 and 1 is 1. So that's where I started. But then since I saw that it's not a good estimation, so I want to move my point closer and closer and closer to 1. Okay. At this tables here will help us find the slope of the secant line of other PQ, of the slope of other PQ lines. Given P is the original point, and Q is a new point whose X values is 0.3 away from the original point, or 0.2 is, or 0.2 away from the original point, so on and so forth. And you can see that in these tables, we have delta X, which is the distance between the X values of Q and P. And the distance here is decreasing from 0.3, 0.2, 0.1, and 0.01. Okay. It's very similar to removing this point closer to the point X equals to 1. And then once we have this distance, we can find the new point Q by adding X, which is 1, plus the delta X, which is 0.3 for this side, right? And then F of 1.3, if delta X equals to 1.3. And this is what we have down here. So the values, the original values of X is 1, and the delta X is 0.3. And we can use this information to find the new point Q. And since we know P and Q, and we know the formula to find the slope of the secant line PQ, then we can find the slope of PQ on the last column here. So if the delta X is 0.3, then the slope of PQ is negative 0.707. So this is the slope is negative 0. No, this is not the one. The slope of the point, let's see if this is 0.3 here. (1.3), then slope of this line, negative 0.707. All right. Okay. And then if the delta X is 0.2, then the slope of the line will be negative 0.66. If the delta X is 0.1, then slope is negative 0.617. And if the delta X equals 0.01, which is very, very close to 1, then the slope of the secant line PQ is negative 0.581. So we could see that as we move closer to the point, the original point, the slope of the secant lines is a good estimation for the slope of the tangent line, the original tangent line that we're trying to find. Okay, so using this table, you can see that the slope is kind of increasing, right? So it increasing, and which makes sense. The slope of the red lines here is steep on the negative side, and then eventually it's go up here, and then it's go up here in order to match with the blue line. So then look at this table, we can guess the slope of the tangent line to this curve at X equals 1 is negative 0.58, which is our guess. So in this example, you can see that finding the slope of the secant line is a topic in is a topic in pre-calculus. And then as you find a bunch of slope of the secant lines where the distance of those points are close to each other. And you're going through a process of finding a lot of slopes when you decrease the distance delta x to estimate the slope of the tangent line at x equals to 1. The slope of the tangent line at x equals to 1, the one that we just estimate, is the result of calculus. And the process that we use in order to estimate the slope of the tangent line is called the limit process.